I was very pleased that Eric agreed to do this presentation for us. Eric is an astronomer at the National Center for Supercomputing Applications at University of Illinois. And he looks at galactic nuclei, so like the disks orbiting the supermassive black holes in the center of the galaxy. He has a tremendous background in working at not only Vera Rubin Observatory, but the Dark Energy Survey, the Sloan Digital Sky Survey, which many of us as teachers have probably used, and PanSTARRS, the Panoramic Survey Telescope and Rapid Response System. So I give you Eric.
Hi, it's great to be here. As already said, I'm Eric Morganson, and I'm going to talk about the Vera Rubin Observatory and kind of more from a researcher's angle and talk about how astronomy's biggest data set is going to change really everything in astronomy and hopefully a lot of things in science education. Oh, sorry. And one thing, I wasn't able to log in for the first 20 minutes, so I don't know if this has been covered. But there's a little confusion on the name. Formally, this telescope and the data it makes were called LSST, the Large Synoptic Survey Telescope. You might hear a lot of scientists who've been around this for 10 years revert to that. Right now, the telescope is now called the Vera Rubin Observatory, but the data it makes is still called LSST, but now that's the Legacy Survey of Space and Time. And Vera Rubin was an astronomer who measured galaxy masses and discovered strong evidence for what we call dark matter today, but was unappreciated in her time. So a quick outline. I'm going to talk about how optical astronomy works for a researcher, how the Vera Rubin, the VRO is really going to change the whole game, what we want to learn as astronomers from this data set, and particularly how you can see the data. So how optical astronomy works. In optical astronomy, we typically start with what we call surveys, which are just big maps. This is a particularly pretty map. It's made by PanSTARRS, one of the projects I work for, which is a telescope out of Hawaii. And it's a map of the night sky covering the the northern three quarters. And you can see kind of stretching in a loop across the middle. That's the galactic plane, the plane of the Milky Way, kind of distorted by when you map a sphere onto 2 dimensions. And if you were to zoom in on this image very, very far, you wouldn't just see, it would be more and more detail all the way down. So you'd see literally hundreds of millions of stars and galaxies. And when you start with those hundreds of millions of stars and galaxies, you have a lot of interesting targets to look at. So specifically when I say target, I mean something to look at with a different instrument. So for reference, a survey instrument, and this is a survey instrument that would make a survey like this, SDSS, is usually kind of person-sized or small room size. This is a small telescope that made a big survey, and a follow-up telescope is going to be big and expensive. The Subaru is this 8-meter telescope on the right. You can see in the front there's a garage door. There's a fence that's probably around 8 feet tall. So this telescope is actually the size of a small a basketball arena. And the big difference between these small telescopes and the big telescopes is that the big telescopes are much, much more expensive to use. And so you only use them on really valuable data sets. So here's an example of just some targets that were discovered on the smaller telescope in bottom and then re-examined in the larger telescope on top. So this is the same area of the sky, the same galaxies we're looking at. And in the bottom, for instance, in the leftmost image, you can barely see anything in the bottom image, which was where this object was discovered. But then when they use the bigger telescope to get a deeper, better image, you see all this detail and this swirl of the galaxy and a bunch of neighbors. And that's going to tell you a lot more as a scientist, or and it's just a lot more interesting, richer image to look at. There's other things you can do after you discover an interesting object in a survey. One thing we often do is get many, many observations. So if we had a supernova, this is a simulation of a supernova on the left. Unfortunately, nothing ever looks that cool in real research. But what we really would get is just a brightness, a plot of what the brightness was versus time. So that's kind of what the data is going to look like on the right. That's what we call a light curve. of this object getting brighter and brighter, brighter, and then dimmer and dimmer, dimmer as it fades. And so that's another kind of expensive thing you could do with an interesting target. You could also get observations from many different types of astronomy. So optical astronomy is often the backbone of astronomy. It's where most of the action is. That's where the stars are the brightest. But there's lots of other instruments that are not optical. For instance, the ALMA radio array is a giant radio array in the Chilean desert. The Chandra, that's on the left, the Chandra Space Telescope is an X-ray telescope in space. And those are going to give you very different information than you get from just the optical. And there's also a spectrum on the lower right. So this is detailed information, color information of what every wavelength from a particular object is doing. Particularly that gives you lots of information about what atoms are present in that object. And so how does VRO change all this? So one maybe counterintuitive thing is that big telescopes tend to have small fields of view. So for reference, the sky is 40,000 square degrees, 360 degrees in a circle. If you make a square of that on the sky, it turns out a sphere is around 40,000. The moon, if you look at it, only covers 0.2 square degrees. And a large telescope, most of them cover about 0.01 square degrees, so even smaller than the moon. So if you were, with a typical large telescope, if you were to try to cover the whole sky, it would take about 4 million images, which might take around 12 years of constant observing. But the VRO is different. So the VRO is much, much bigger than the moon. You can see this is a typical what a typical VRO image would look like with the moon, moon much smaller. You can actually fit about 40 moons in a VRO image. So a VRO image is 9.6 square degrees. It would only take about 4,300 images to cover the whole sky, which VRO could do in 5 nights, as opposed to 12 years. So that makes covering the sky just a practical, relatively easy thing to do. Of course, the details of what VRO is exactly going to do are a little different. This is what the legacy survey of space and time, the data set, is going to look like. This is a map of the whole sky projected on 2 dimensions. And because the VRO is in Chile, it's going to look at the southern sky. And over most of the sky that it looks at, it's going to get about 1,000 observations. You can also see, in addition to the southern blue blob, there's a little spur coming out of the south. That's actually the galactic plane. So that's a bit of the Milky Way that they wanted to observe, even though it's in the north. And you can see another green blob on the left. That's the ecliptic. So that's the plane of the solar system. So that's where we might want to find more asteroids. The advantage of this survey is not only is every image going to be deeper than any other survey image, it's going to be like, it's going to be a proper big telescope image that we used to have to only be able to afford to use on particular targets. But you're going to get 1,000 of them. You're going to get in different colors, so you'll get color information on every single object, and you'll get time information. So for just a single supernova, you'll be able to see it get brighter and dimmer just with the VRO data. You won't need to use any extra data, which means that we're actually going to be seeing basically every supernova in the southern sky. So you could ask, why didn't we do this years ago? Like, why didn't we just get the good data everywhere? That seems really obvious. But there's some few engineering reasons. So a large mirror is expensive. This is actually people sitting around the LSST mirror before it was silvered. And you can see it's enormous. It's 8 meters long. So just making that object is expensive. And for engineering reasons that I don't really understand, a mirror with a large field of view is much more precise and harder to make. And so that, of course, that means that's more expensive too. So a large mirror with a large field of view was just super expensive, something like $200 million. And relatedly, if you have this giant mirror and you have this giant telescope and it has a huge field of view, you need a giant camera to just take in all the data. And the giant camera for LSST was also something around $200 million and was probably impossible to construct before about 2010. I'm not really much of a telescope technology person, but just showing basically how it works. This is the LSST kind of telescope rig on the left. So this is before the mirror's been put in it. And this is a diagram of what's happening on the right. So the light comes in, it bounces off the primary mirror, the big mirror, gets reflected to a secondary mirror, a smaller mirror suspended above the big mirror, goes back to what we call the tertiary mirror, but is really just a carved second surface in the primary mirror. And then finally it's reflected, that's a third reflection up to the camera, which is supported above the main mirror. And the camera, which is I think is more interesting to me at least, is the biggest camera in the world. It weighs about 3 tons. Just the lens to the camera is 5'5", so a person could walk into this camera. And it's 32 million pixels, which is about 267 iPhones. Each image is 6 gigabytes, which means that in an hour you take about 540 gigabytes of data. That's large enough to fill up the largest hard drive you can get on a MacBook Pro. In a single day, you would fill up about 20 MacBook Pros, 10 terabytes. And over the course of a 10-year survey, we'll fill up about 60,000 MacBook Pros. Of course, we're not literally saving the data on MacBooks. You may have noticed that I work at a supercomputing institute. There's several big computing institutes that are going to be in charge of managing all this data. But all this data will be about 10 times bigger than all the astronomical data currently available. Okay, so let's get on to the science. What are we going to learn? The short answer is actually, if you want to learn something in astronomy, LSST is going to teach you something, because it's just taking images of everything, and it's going to take great images of everything. But LSST has kind of committed to 4 core projects that they want to make sure get a lot of research. So the first is cosmology. In this picture on the left, we have kind of this map of the Big Bang is on the left, and during the Big Bang, the universe was kind of a uniform ball of gas. Everything was uniform, just a uniform ball of gas, essentially, almost like a giant star. And then as time went on, objects clustered together, and you particularly got galaxies and clusters of galaxies. And this clustering, this structure evolves as the universe keeps going from left to right here. And the image on the right is kind of what an LSST image will look like. And you see here just hundreds of galaxies, and we can determine how far away the galaxies are from their color, and see how they're clustered just by where they are in the sky. And then we can really see the clustering of course, how in an astronomy setting, how far away is also how old you are, because these objects are going to be 10 billion, or up to 10 billion light years away. And so by seeing how the clustering changes versus time, we're tracking the structure history of the universe. And that also tells us about how the universe has expanded. One subject that I really like is called Milky Way archaeology, or it's kind of the history of how the Milky Way was formed. So on the left is a simulation of how galaxies are formed. They're formed by many, many collisions of smaller galaxies. And these collisions leave a lot of mess around. This mess comes in the form of streams and spurs of stars that extend off the main galaxy population. And we've actually started observing some of these streams. On the right, you have an image of the full sky, and you can see the plane of the Milky Way kind of cracking, going down from top to bottom. And this red-yellow spur off to the right, and this other yellow-green spur off to the left, those are actual streams of stars that were kind of liberated from the main Milky Way galaxy during collisions. So LSST is just going to find tens or hundreds of those all over the place, and really give us a history, and we'll be able to track kind of the history of how the Milky Way formed by looking at these streams. LSST is going to find 90% of asteroids bigger than 140 meters. So we find asteroids by just looking for things that move. They'll kind of look like this picture on the left, where there's a dot moving from left to right in different images. And we already actually have a few 100,000 asteroids tracked down from other surveys. That's what you're seeing on the right, is the population of all the asteroids currently known in the solar system, but LSST is going to increase this by about a factor of 10. In addition, one interesting fact about finding asteroids is that you can actually prevent the Earth-destroying asteroid from hitting us, because most asteroids that would hit Earth are actually following us along right now in an orbit fairly close to us, and will have a predictable path to when they'll hit us in 10 years or 10 years or longer. So if we were to send a rocket to an asteroid and nudge it 10 years in advance, you can actually prevent it from running into us 10 years along the road. So it is potentially the possibility that LSST could save the entire planet Earth. So another big component of LSST are what are called alerts, and that's really anytime something changes on the sky. Usually that means something glowing brightly. So these are two simulations of cool events that we might see. Sadly, it'll never look like this in the telescope. It'll look much more just like a dot getting brighter. But types of things we want to observe are on the left. This is called a tidal disruption event, which is a star swirling into a black hole and getting ripped apart. And on the right, we've got two neutron stars spiraling into each other and exploding before they become a black hole. And right now, in both those cases, we've observed a few objects like these, but LSST will just find hundreds and thousands, and we'll certainly find objects that we haven't even imagined yet. And how you can see the data, I'm probably the person who knows the least about this, so other people will give you better information, but just 3 things that I wanted to point out. LSST has a yearly release, so starting in around 2024, they will release just maps of the best maps you can possibly get of most of the sky. These will be the same pixels researchers use. It'll look a lot like this type of data that's from a previous survey, Dark Energy Survey, where you can see there's just great detail. This is a random patch of the sky, and then I zoomed in on what looked like the coolest galaxy. You can see there's a lot of detail, and so LSST will be similar to this, just better. If you do want to go get DES, that's the URL to get DES data right now that you could look at. There's public alerts. These alerts for when things go boom in the sky can all be sent out publicly. As a just random user, you can receive the actual image of the thing that's getting brighter or dimmer, its brightness and its location. And you could say, I want every observation of this object. Or I want you to send me every new supernova you find. That would actually be a bad idea because LSST is going to find something like 1,000 supernova a night, or every observation of a particular asteroid after it's been discovered. And these will all be available as download, email, and I think there's a lot of work going into making them texts and tweets and other easy ways to receive information. And a final way to interact with LSST data is the Zooniverse, which is a website that's got multiple astronomy and non-astronomy projects where citizen scientists, just users, can classify objects and determine what they are. So I picked an example of figuring out what type of galaxy this is. It's fun, easy, clicky, and addictive. If you sign on right now, in 2 minutes, you could be actually doing real science. It contributes to actual discoveries. And pretty soon, once LSST gets going, I think astronomy projects will just be dominated by LSST data because that's where so much data will be from. That's all I got. I would love to answer any questions.
All right, well, we have a few questions for you. So if you can do the North Ecliptic Spur, why doesn't the survey cover the rest of the sky at that declination?
When a telescope looks very far to the north or very far to the south, you're looking through more oxygen. There's more air mass, is the term we have. Not oxygen. You're looking for more atmosphere, so there's more air mass. So you actually get less depth. So it's most efficient to look straight up, which is why LSST is focusing most of the observations kind of at similar latitude to the observatory.
Okay. Another question was, what was LOR standing for?
LOR, that sounds like a typo. I'm sorry.
So, who asked that question? Let's see, that was asked. Who asked that question, go ahead and unmute and ask it again if you were asking. David Dixon, you asked that question.
Yeah, apparently I just missed the
VR.
letters or the words for the letters LOR.
Okay.
I don't know what LOR is.
Was it for VOR?
There's VRO. I think the only two things I tried to say were LSST, which is the survey, and what we used to call the telescope, and VRO, which is the actual telescope.
Okay, I must have misheard. Thank you.
Okay. The next one was, they're asking if we will have access to the presentations. Are you going to be sharing those?
I am happy to. I sent this to Artis. If there's a different place to send it, I'm happy to. I'm sure. Well, I can't actually speak for the other presenters, but I'm pretty sure they'd all be happy to share them.
And I'm thinking we can probably attach those to the page.
They're going to be attached to the speaker page, but we didn't want to do it until after each person did their presentation.
Right. And 2 more questions, or well, 3 now. Do you have any updates on how the new constellations of satellites will affect observations with VRO?
It's not great. My understanding is things are getting a little bit better with the painting, and it is not the satellites are primarily a problem at twilight, in the morning, in the afternoon, and at night and in the morning, and that's actually the least useful time. That's often used kind of to calibrate the telescope rather than to do proper science observations. So we'll be able to get by, but it is very frustrating.
How will LSST data complement the James Webb data?
James Webb, in kind of the way I was talking about, James Webb is a small telescope that's it's small telescope in the sense that it can really only look, I think its field of view is something like 1/10 of a square degree by 1/10 of a square degree, as opposed to LSST, which is 3 square degrees by 3 square degrees, so a factor of 1,000 or something. So James Webb will be a follow-up instrument for LSST observations. Particularly, LSST will discover a lot of high redshift things, a lot of galaxies at redshift 6 or 7, and James Webb will be the perfect instrument to get much more interesting and instructive data from those objects.
Okay. How can I incorporate existing SIT-SIC projects with VRO data?
Existing, I don't know.
CIP, SIC, Padma, this is yours. If you want to pop in.
It's probably
citizen science.
Yeah.
Oh, citizen science. So the important clarification that there is no LSST data yet. It'll come out in 2024. I think, I know a lot of projects are going to be working on this. It will be relatively easy if you have a object of interest to just type into LSST, hey, give me the best image you can for that location. So that'll be something that LSST can provide, even if it's even if your data is coming from some other source. But I think other people would be better at talking about citizen science generally than I would.
Okay. So last question, what filters do you use in the near IR, and how far in distance do you think we will see?
So LSST for filter heads is 6 filters, meaning it looks at light from 6 different bands, and it's UGRIZ. U is slightly into the ultraviolet. I think it goes down to maybe 200 nanometers. Oh, UGRIZY, I don't know if I said Y. And Y goes very slightly into the infrared, just about to 1 micron. So LSST, there are telescopes that go out to a few microns from Earth. You don't want to go you don't want to go too much farther than that because the atmosphere absorbs things. So LSST is just going a little bit out into the infrared. So, if you detect an object in a Y band, in just the Y band, the reddest filter, you can actually get objects up to about redshift 7.2.
Okay, thank you.